Thank you, Maz, for your introduction. Okay, thank you, Maz, for your introduction. It is my pleasure to join you today during this webinar hosted by Diana, Finite Element Analysis. Good afternoon for some or good morning for others. I am Ezzeldin Kamel, Mohamed, researcher at Construction Research Institute, Egypt. And today webinar, we will discuss an idea of hollow dam named bubble rolled compacted concrete dam. The bubble rolled compacted concrete dam was published as a poster at ICOLD conference 2019 at Ottawa, Canada. My co-author is a Professor Ihab Khalil, Professor of Structural Engineering and Head of the Construction Research Institute. I want to acknowledge my co-author, Professor Ihab Khalil, for his effort and Construction Research Institute for funding this research project. Finally, I want to thank Diana team for hosting this webinar and giving me the chance to share our research results with you. And this is a published poster. Today, we will go through brief about dams, types, then load pass within dam body, methods of material rationalization, and research questions. Then we will discuss deeply the proposed idea of bubble rolled compacted concrete dam, which will cover CPG analysis, coupled stress analysis, time history analysis. Later on, we will discuss our proposals for construction and our current research work discussing hollow dam. Finally, conclusion and recommendation. Before going to rolled compacted concrete dam, I want to introduce myself to you and share with you most interesting project I got involved with. I got my bachelor degree in civil engineering from Cairo University by 2009. By 2012, I got my master degree, which was discussing live load distribution factor for slab girder bridge and box girder bridge according to Euro code and Egyptian code. We proposed a 20 equation for covering large parametric study and correction for skew angle using multilinear exponential regression. Then by 2016, I got my PhD in structural engineering, discussing aerodynamic stability of ultra long span cable suspended bridge. The central span of this bridge was about 3,300 meters, where we discuss the bridge deck behavior under wind load and work on optimizing deck shape. In addition, we developed an approximate analysis for analyzing three-dimensional suspension cable using ANSYS Fluent and SAP 2000. By 2018, I got a postdoctoral at University of New Mexico in the United States, and I was working in computational mechanics and hybrid testing of nano-modified composite under extreme loading event. If you are interested about these research topics, it will be my pleasure to share with you more details. Now, I want to share with you major work I was involved in. Most of my work is related to infrastructure, dams, and hydraulic structure. I got involved in the assessment of regulators, pump station, large-scale barrage, divergence dams, navigation loop, and my tasks were changed from project to another, and it covered field investigation, structural assessment, rehabilitation, and construction inspection. And this figure shows numerical analysis of a Boolean regulator using Diana software and SAP 2000 as an example. And this mood shapes of the same historical regulator, which has around 100 years old. After being involved in the master plan of Egypt of structural assessment of 150 regulators in Egypt, we published the paper under title Innovative Solution for the Repair of Hydraulic Structure, especially regulator, discussing non-traditional solution for repairing of hydraulic structure. We discussed the rehabilitation of plane regulator as an example. Now I want to show you a quick look at my major models I have done. Continuing the hydraulic structure, I was involved in assessment and review 3 main dams and 2 divergent dams. And here the models of navigation log using solid element based on the client demand. On the right, you can find a double navigation chamber, and on the left, you can find single chamber navigation log using SAP 2000. Now, I want to share with you the 2 most interesting projects I worked on. The first was the assessment of historical Patros Masonry dam, and the second was assessment of historical masonry siphon. The age of each structure is exceeding 100 years old. In continuing masonry work, I'm working with my colleague Mohamed on assessment of leaf stone masonry walls, and you can see by our experimental work where we are comparing different nonlinear material models for verifying the work. As you can find, comparing the results comparing the results at the left with different LVDTs, vertical and horizontal. This study will cover the dynamic behavior of this type of walls, and we are working on the assessment of Muhammad Ali Palace. It was constructed by 1808, and also we are working on assessment of Sultana Malak Palace, 1915. It is a chance to thank my colleague Osama Amir, assistant lecturer at Conservation Department, Cairo University. Referring to my PhD thesis, this is a part of my PhD models using ANSYS Fluent for analyzing aerodynamic forces acting on the bridge, and the structure analysis using ANSYS or SAP 2000. On continuing my work, I worked with my student on the assessment of different bridges. You can find here assessment of damage in precast segmental bridge at Kuwait, and continuing the research with my students on stability of cable stay bridge under sudden failure of a cable and suspension bridge. Also, we studied multi-band suspension bridge and high cable bridge. During my postdoctoral at the States, I worked with Professor Fernando Moro, Assistant Professor of Civil Engineering, Construction and Environmental Engineering at University of New Mexico on the assessment of timber railway bridge. And we studied of losing bracing members. Finally, I worked on minimizing the risk of failure of pile bend pier under seismic loading by grouting using Diana software. This work has been already published under the same title. Sorry for my long introduction. Hope you like it. Going back to our today webinar, our topic under name bubble rolled compacted concrete dam and an idea of hollow dam. As you know, dam is a structure which prevents the flow of water and accumulated in a reservoir. But from point of view of structural engineering, it is a structure for retaining water horizontally, and this horizontal pressure transferred to the supporting system depends on the dam type. For example, earth-fill dam and gravity dam transfer the water pressure through the dam body to the ground as shown in figure. And for the arch dam, it transfers the horizontal pressure to its abutment, which is usually hard rock. However, for the buttress dam, the load transferred from the upstream face, slab or arch, to the buttress and to the ground. The selection of the dam type depends on different parameters. We cannot cover it today. However, the material rationalization and its impact in cost is a major factor. For example, stress distribution in trapezoidal dam body. Stresses in the middle part of the dam are lower than the outer face, and all are almost compression. However, under extreme loading, stresses at the upstream face go higher and converted from being tension to compression. It can be concluded that large part of the dam is stressed with the lower stresses. So we think about redistributed stresses and increase stresses in a specified zones and generating voids within the dam body for decreasing the consumed material. Studying the dam type found that the designer think about two major ways of cost reduction based on material rationalization and the statistical system of the dam. We can find that in arch dams and buttress dam, designer reduce the solid amount of dams and find certain passes for the loads. On the other hand, for the embankment dam, it's usually used in situ filling material, rock or earthfill, and the type of earthfill dam is developed to be concrete face dam. On the other hand, especially for the gravity dam, designers think about using low cemented concrete as the rolled compacted concrete instead of conventional concrete, and it covers cemented material and cemented sand gravel and rock fill concrete dam. In fast review, cemented material dam was firstly introduced by 2009. It usually uses its major advantage is using in situ material and low cemented material. The aim of this dam is to design a friendly and economically dam. Which is mainly affected the concrete strength, which is lower than the usual RCC. For the rock fill dam, it was firstly introduced by 2003, where it used large size of rock greater than 300 millimeter and require high performance self-compacted concrete. It can be considered as a kind of a masonry dam with the advantage of concrete dam as decreasing cement compensation, low temperature rise of hydration heat, reduced shrinkage of the concrete. In conclusion, designer work on optimizing the dam cost and speed the construction. So we formulate our research question as follows. As a strat and time method, is it possible to generate or specify a load path within the dam? Regarding to cost control, will this process feed in the cost reduction due to construction limitation? Does the construction process would be affected? And how to optimize the loads? Firstly, we think about domes and arches, where loads can be easily transferred, and we started our work about load transfer in different kinds of structure as follows. Looking in the history, we find that the ancient Roman used arches for building spans, and it is shown in the aqueduct of Segova, Spain. It was constructed around 537 before Christmas. Also, then the revolution of domes and vallet. Finally, with the modern century, the hollow core slabs, which is already available in precast forms and post-tension slab. This picture from Alibaba website has a table of precast hollow core slab. And finally, designers developed bubble slab. The common idea of this different application is that they removed the low stressed area and generated passes within the structure for transfer loading. This has a great effect on cost reduction. However, it requires high quality control. In dams, designers try to achieve the concept of making void within the dam for decreasing amount of cast-in-situ concrete according to construction and decrease the total amount of concrete. So they propose the slotted dam as shown. They generate a slotted void within the dam. In a slotted dam, the ratio between the slot width and the monolithic dam based on existing project varied from 13.6 to 45%. And for the hollow dam, the hollow part is highlighted by red, and the part in blue is an inverted bucket. Where hollow dam can save cost by 11.86 to 24.7 based on existing dams. Also, the dam hollow can accommodate a hydropower plant for overcoming the conflict between the planet layout and flood. Other forms of hollow dam is the buttress dam, which can save large amount of material. However, it requires lots of formworks. In optimizing the design, designers work on the buttress head, and they found that the diamond head tension and compression stress are lower than massive head or rounded head. As you can show, there's a tension decrease in the diamond head. And they studied different types of massive head, as you can show, different of them. Also, for the Mesan Dam project, the designer think about generating a hollow within the buttress inside, and there was a drainage pass inside. It's hit about 88 meters. In conclusion, the use of arch may improve the stresses distribution. The concept of hollow dam are adaptive to the even settlement of the foundation. The lower portion of the dam has less concrete placement amount, which helps in accelerating the construction. The front and rear legs can be constructed independently, which helps in large exposure area for dissipating hydration heat during construction. However, the formwork and steel reinforcement are higher and will offset rather portion of the cost saved by concrete reduction. The challenge is how to generate void without increasing the formwork or reinforcement. So, our research idea is to use arch action and domes where vertical load and horizontal load transfer around the dome in compression and tension. Usually for the domes, it carries vertical loads and transfer it vertically to its supporting. However, the proposed bubble will carry horizontal and vertical load. So the proposed resultant stresses would be lower value of tension and compression. In the beginning, we think about generating a void in elliptical void within the dam. But constructing such void, this elliptical void, two main elliptical void, but constructing such void will require extensive form work and reinforcement. So we think about distributing spherical shapes within the dam and called it bubble rolled compacted concrete dam. This is our configuration of the bubble rolled compacted concrete dam. We distributed bubbles with 2 meter diameter placed in a staggered arrangement as shown in the figures. So it is staggered. And to consider the change in the dam cross section, the analysis focused on one segment of the dam with 20 meter width, where 3 bubbles were placed within 6 meter center to center in the longitudinal axis of the dam and 8.25 towards the downstream. Going up, the bubbles were placed staggered as shown. And for eliminating the leakage of water within the bubbles, a drainage system were proposed for dissipating the drainage water or leaked water towards the downstream. As you can see this system. Then we use Diana finite element analysis software for the numerical modeling, and here is the numerical modeling description. In the numerical modeling, 2 dams were modeled within the same material and boundary condition. The model description was 40 meter height and the foundation depth was 100 meter, greater than the double of height of the dam, for ensuring that bubble of stress within the foundation. The mesh were fine in the dam and get coarser going to the boundary condition. Also, the mesh size were small for detecting the bubble geometry. So you can find that we have a large number of elements for the dam, around 50,000, and for the cut of 40 elements for the foundation, it's about 700. The numerical analysis cover self-load, hydrostatic water pressure, and time history seismic analysis. And the analysis cover steady state groundwater analysis, structural nonlinear analysis, modal analysis, transient analysis, and we are working on heat of hydration analysis. Discussing the results, now we will discuss the results. First, we will start with seepage analysis. But in the beginning, we will start about seepage foundation. The upstream head was 40 meters, and the downstream head was 0. The potential head at the bubble was 0 to allow water leakage to the bubble. And we cannot simulate the drainage pipe within the dam. So we just stopped by assuming that the boundary condition in the bubble are 0, because it's very sophisticated if we wanted to simulate this drainage system within the solid model. Seepage results show high efficiency for the bubble in collecting leakage water, as shown in the section A at the center line of the dam, and section BB at the outer bubble center line. And in comparing the results of full dam and the bubble, it is clear here that the phreatic surface shows significant change. In the bubble dam, water head was dissipated by the first column of the bubble, where it is continued to the middle of the dam at traditional full dam. Also, the first row of the bubble helps in decreasing uplift by 2 meters. The pore pressure within the dam body also has been affected. So we can find that the pore pressure decreased by dissipating the leakage water at the first column of bubble, and the horizontal section at 4-meter height shows this significantly. For the static analysis, in the horizontal deformation, there is no significant difference in deformation at the foundation level, where even inside the dam or on the outer surface of the dam. This is the horizontal deformation at base, and you can find that the difference is not significant. The same for the total deformation at foundation level. The change of deformation within the dam body is insignificant. Continuing with the static analysis, the vertical stresses at the dam foundation decreased by 30%. As you can see, changed from 0.91 to 0.69, and the high stress area decreased. This is high stress area decreased. For the horizontal stresses at the foundation level, both the same are within the same range. However, stress area go higher, going up at different horizontal level and vertical levels cross section of the dam. Our is already achieved. That stresses are increased around the bubble, especially located at the first low and first column of the bubble. In comparing these results with the full dam, it reaches this high stress. However, the stress area are lower than the area of the bubble dam. For this, we can find the stress area for the same certain value is higher, but in the full dam we have the same stresses. So what happened is that stress area increased, but within the same range. In the mood shapes or modal analysis, the dam mass decreased by 11%. However, it didn't affect. However, the uniform distribution of bubbles has no significant effect on center of gravity. But we can find that the sway bending frequency decreased. The first sway bending frequency decreased from 6.3 to 5.9, and the second sway bending decreased from 22 to 19. Also, we can find that there is a cup point. Change in the cup point is not as significant. But for bending, the major bending direction frequency, natural frequency increased from 7.3 to 8.31. That means it is increased by 11.3%. For the first and second bending, first bending increased by 11.3, and second bending frequency increased by 200. Moreover, in the second bending mood, the mood shape cup point raised from the first third to 2/3 of the dam height, which is great change and affects the dynamic time history analysis. In time history analysis, transient analysis, we studied the behavior of the two dams under time history load, and we can that the response is different. We studied 4 points on the dam height: 0, 10, 20, 30, 40, the crest, and we can find that comparing at height 10, there is no significant change between the deformation of the dam. However, at crest level, the horizontal deformation for the bubble dam about double times of the full dam. This is an agree with other analysis which showed that the cut point raised from third height to 2/3 height. This is the cut point change in the location. And this is the deformation. We choose time 12.4 seconds because it's the location where large deformation occurs. In the stresses, we can find that shear stressed area increase around the first column of the bubble, and stresses near the downstream. However, the stress near the downstream have the same value. For the principal vertices, tension stress increased around the first row of bubbles and concentrated around it. And comparing the results with the full dam, tension stress is increased higher, but in this certain area. The principal stresses, we take a section at first row of the bubble and find that the tension stresses increased at the first row of the pile and it decreased gradually towards the downstream. But after our analysis, we find that we can assume that there is a neutral axis location. It didn't change from the two types of them. The same thing happened for the second column of bubbles. We can find that the stresses increase around the bubbles greater than the full dam, but it's just all of them are lower than the allowable. And thinking about the construction, we know that we have a different limitation and we have different concerning for the construction that we need construction. We have a construction challenge, construction speed, construction cost, and the quality control. In our work, we propose 3 methods of the construction for the bubble. But today in our webinar, we will discuss only one, which is the most suitable for the construction, and it is a precast boxes. In order to simplify the process of bubble inside the dam, cubic precast with inner spherical void are precasted and placed in their location, as you can see. In this method, the rolled compacted concrete were compacted using traditional roller compactor. The use of the precast concrete blocks will decrease the required cast-in-situ rolled compacted concrete by around 30% of the cast-in-situ. That would increase the construction speed of them. Shear connectors should be considered in the outer face of the boxes for increasing the friction surface and ensure enough bonding between precast concrete and cast-in-situ rolled compacted concrete. However, placing drainage pipe connecting the boxes is a complicated issue for this construction. So the use of low permeable concrete in the precast boxes will minimize the probability of filling this bubble with the water. However, it will prevent water from going inside the bubble. Now, it is our recently work. We are working on a hollow types of them. We found that the construction of bubble may be more complicated and it will affect the construction. And on the other hand, generating void within the dam may reduce the factor of safety. So we think about generating slender voids. In this slender voids, we can fill it easily by infill material as a soil for not affecting the factor of safety of the structures. It is not affected dramatically in the bubble dam. It just reduced by 0.1%. But in order to overcome this and construct it more faster, we think about placing precast cylinders, which will not affect the construction process because there is a lot of gaps between it, and we can construct it easily. And at the top, we will use dome action for transferring the load from the upper concrete to the lower. We're working on the analysis. In conclusion, the bubble rolled compacted concrete is a novel proposed for rationalizing material and first introduced in this research as a bubble. The use of the bubble rolled compacted concrete rationalize about 12 of the required rolled compacted material with no effect on the construction speed. And the use of the precast box minimize the placing of rolled compacted concrete by 32.5%, which will increase the construction speed of the dam. The bubbles act as the drains, and the first column of the bubble dissipates the leakage water. The shear stress between the dam and foundation are not significantly affected. However, in time history analysis or seismic analysis, stress increased, but still within the allowable range. Our future work was a parametric study for the bubble dam to optimize the material rationalization, and it can cover the following aspects: bubble size, bubble arrangement, precast block size, effect of the precast size on the dam, bubble effect on heat of hydration dissipation. The hollow dam using cylinder may be suitable than bubbles due to construction issue. The cylinders are proposed to precast concrete as a permanent form and can be placed with small heights. Regarding to the construction, that we can make a cylinder precast with 1 meter or 2 meter and place it above each one. The idea of the bubble rolled compact concrete dam and the technique of the precast forms light up the idea for partially precast dams. Thank you all, and thank you, Mel.
So I would like to thank you all and wish you a pleasant day. Thank you. Have a good day.